Morning.
Morning.
How we doing, y'all?
It's not morning. Good afternoon.
I say good morning. I always say good morning. Hello, everybody. How's it going? How's life?
Good.
Good? We're alive?
Yes.
Oh, wow. So much enthusiasm today.
Yes.
Last time I saw you, it was your birthday.
Yep.
Anything fun?
No. No.
Oh, that's good. You had a good cake then?
Yeah.
Yep. That's good. That's good. All right. Today we're going to talk about pointers, memory, and linked lists. And this is all very interesting stuff. I was just chatting with Dr. Neat. He thinks I'm wrong, but I'm going to lecture on it anyway, and I'll correct it later if I'm wrong. But pointers and memory are very interesting in Java, and I'll talk about that in a second. So we had this conversation at lunch, so we'll see if I'm wrong. I'm going to continue lecturing on what I've been lecturing before to keep it consistent. If I need to correct myself, I'll correct myself in all 6 periods. But let's do a review on stacks and queues. And I think it's great that I might be wrong. It's good. I'm learning too. But let's review on stacks and queues. Stacks. What is the rule for stacks? Top down, which is pancakes, which is yes.
Last in, first out.
Last in, first out. Fantastic. So stacks are last in, first out in that I have a pancake, I put it on top, I eat that pancake first. What is the rule for cubes? There's a rule name for this. Is this because you were working on your homework last week?
First in, first out.
First in, first out. So we have LIFO and we have FIFO, right? LIFO's for stacks, FIFO's for cubes. First in, first out. It's a line. You have the first person going in, the first one's going to be out. So stacks and queues, fantastic. Now we briefly talked about this last week where we had this giant chart up on the whiteboard. And this was the interest in that this is the list interface. List interface has all these things that implement it. And in a difference to an array, what is so special about this? There's 2 things I'm looking for. There are 2 things that lists do that arrays don't do. What is one thing? Any guesses?
Oh, I think I know both of them.
Let's go with one and I can ask Charlotte the other.
Okay, what if the first one is wrong, then can I resort to my second one?
I'll go you, Charlotte, then you.
Okay.
What do you think is the first one?
Like what the difference is between an array and a list?
No, what is something that this does? What does a list do? What is one thing that a list does? And it's good to compare against an array because
Dynamically stores memory.
kind of. Yes it does. Not quite what I'm looking for. What do you think it does?
It uses addresses.
It dynamically stores memory, same thing.
You can change the size.
That is the other one. Where, yes, you can change the size, and I'm looking for specifically, you can add things, and you can remove things.
Okay.
Those are the 2 things I'm looking for. I'm looking for add and remove. All of these things here can add and remove things, right? They can all add and remove things. Array lists, you can add and remove. You can insert, you can delete stuff. You can do stuff in different places. Array lists are really nice like that. Vectors are the same thing. We're going to be learning about linked lists and how we can do an add and remove with a linked list. So, wherever my mouse is. Last week we also learned about arrays and how they're static and that we have to chunk out a spot in memory just for an array. To chunk out a spot in memory just for an array, it has consecutive memory locations, one after another. That's how we learned about that. We've also learned last week that array lists use addresses or pointers to store data. We learned last week that it has a list of these different references and addresses, and these reference actual places in memory. Now I'm going to correct this today, and that this is technically wrong. But we'll talk about that later. But same concept in that we look at things from memory. We store things in memory. The big correction that I'm going to say is that Java doesn't have pointers. Pointers are non-existent in Java. Addresses are non-existent in Java. You can never really get an address in Java if you try to. They just don't exist, and I'll explain the reasoning for this. So Java doesn't have pointers, but instead of pointers, Java uses references. So we use something called references to store values. And we'll talk about what that actually means in a second. Let's put this example up here. So if we create a rectangle, R1, and we create a new rectangle, what is new? So what's so special about new? Yeah.
It means we allotted memory for that object.
Yeah. we've created a new memory location, or allocated a new piece of memory location for our rectangle. We've created a new rectangle memory. Now we create R2 and assign it to R1. And then this R2 here is a reference. It is a reference to R1. Does that make sense? That Java uses references? Now, my question to you guys is, does R1 change when R2 changes? Peter's like, nah. Why? Isn't it a reference?
It's different though.
It's different though. You just think it's different?
Yeah.
Do you know why it's different?
No.
Any other thinking of why? Do you think it changes? All of last period thought it changed. Yeah. I was just thinking about what we were talking about. Everyone's like, no, in
This
this class.
is, I thought it's an R2 referencing R1.
Sure,
So
it is.
R2 is looking at R1. So why would R1 change when R2 changes?
So what if R1 changes? Does R2 change?
That's what I'm not sure about. Doesn't it depend on like when it comes to change? Because if the change in R1 was before, then
That's the question. That's what I'm
yes,
asking.
that's what I
I
believe.
don't think like it would change unless you reassigned R1 to R2 again. Like I think
Okay.
if you changed R2, then R2 changes, but then R1 is like the old R2.
So we'll
Looks like
explain
it's
it.
gotta be.
No, I get what you're saying. Until you reassign it, you're saying.
Mhm.
So, in short, you guys are correct in that R1 does not change when I change R2. And the same is for the opposite. And then if R2 changes, or R1 changes, R2 doesn't change. R2 changes, R1 doesn't change. Neither of them change each other. And this is very specific to Java. This is specific to Java because Java purely uses the pass by value rule. So I'm going to teach you two things today. One is pass by value, and one is pass by reference. And I'll talk about what those two differences are and what they actually mean. So, if we look at this cup of coffee, pass by reference. On the left here, we have a cup of coffee, and we can pass the address of that coffee into a method, and that method can fill up the coffee. Since we pass the address in, we're passing where that is in location of data. They're both the same cup of coffee, because they're both at the same address. Does that make sense? Here, we're passing a cup of coffee in, but we're copying the cup of coffee and passing in a value, a new value. And that cup of coffee is different than the original. And I'll talk more about what these actually mean. We'll come back to this slide. So pass by value means you're making a copy in memory of the actual parameters values that is passed in. So we're making a copy of some value. It is a little confusing in Java because we use references in Java, but references actually are taking a copy of a value. The stack space, we kind of talked about memory and how we have a stack and a heap. In the stack space, if we define two new integers, x and y, x is 1, y is 2. If I then go and say x1 equals x and y1 equals y, x1 and y1 are references, in that they are references to x and y. The way this works in memory is that x1 or x and y are still there, but we copy and pass the value in to x1 and y1. So we copy this value and we copy this value. But they have two new memory slots in memory. And if we change x1 and y1, x and y don't change. This is why rectangle would be the same way. Or rectangle would be, R1 would be x, R2 would be x1. Does this make sense? Now we pass in values and we just basically are copying values. Peter, are you okay there?
Yeah.
Does that make sense?
Yeah.
Cool. You look like you're squinting a little bit. So, same idea. So we're passing in values and we're copying the value. That's what a reference does. Now, pass by reference, or I'm going to call it pass by address. Pass by address means you're taking a copy of the address of the actual parameter that is stored. So we're taking the copy of the address, passing the address, and then we can reference that data depending on what address we give it. So in memory, we send it to a specific address. It does something in that address. So we're not able to use this in Java, but we can use this in C and C++. And we'll talk about examples of this in a little bit. So more example about pass by reference, just to understand it. Say we have object A and we have object B. These are two brand new objects. That's it in memory. We have two different objects. They're all stored perfectly fine. Now, if I have two other objects, A1 and B1, and I pass in by reference, or I give them the address, now we're all addressing the same value. So A1 equals A. They're both references. They're both going to be referencing the same value in memory. Does that make sense? So if A1 changes here, it's looking at the address of where that data is. It changes the data at that address. Does A change?
Yeah.
A changes. Yes.
So when does this occur?
When does this occur?
Yeah.
So I'll show you more examples in a bit. But straight off the bat, if I were to say, because this doesn't occur in Java.
Yeah.
This technically doesn't occur in Java. But if I were to do a C++ and I were to have a method that says, hey, get the square root of this value. In Java, I could pass a value in to this method, and that new value would be a copy of the value I originally had, because it's passing it by value in Java. I would then do square root of the value and return a value to myself. Now, if you think about it in C++, I would pass in the address of that value, pass the reference of that value. In that method, the square root method, I can then square root that value, and it will be changed in the original code. I don't have to return anything. I can just go back to my original code, and that value will be changed.
So let's say int b equals 4, and then we square root it in C++, then b is equal to 2.
Yes. We'll kind of get there. We'll have more examples. But in this case, if I were to say b1 is another object, and we create a new object, it'd be like this. This is also similar to like, these are passed by value. We have two different values. This is passed by reference. We pass in the address of the reference. You see the big difference here? What's different about these two? What's good and bad about this? Passed by value. Yeah.
It takes up more memory space, and more memory space, you have to slower stuff down.
Exactly. So pass by value does take more memory space. So Java tends to take more memory space than C or C++, just because we can do pass by reference. Now I was talking about this with my roommate last night, because he works at Western Digital, which is a hard drive company that does hard drives and storage and everything related to storage of your computer. They use C or C++ as their languages. The big reason for that we were talking about was Java is not used because of how much memory is taken to do pass by value. Because we can do pass by reference, their memory storage company, their storage company, is going to be used to pass by reference just to be way more efficient. Use less memory. Their whole thing is memory and storage. Why would we not use less of it? So it was just an interesting topic that a lot of the hardware companies are going to be using C or C++, and you can go look at that and what languages they actually use. They use C++ because they want to make sure they use less memory. Interesting. It was just cool. A relatable fact. Go back to this beautiful image. We can pass in the address of this cup. We fill up the cup. Both things fill up. We can pass the value of this cup and copy it. We can fill up one, return it, and we have to reassign it. But until we reassign it, that value never changes, like you were saying at the very beginning. Does that make sense? Cool. Now this is a slide just really quickly showing you that you can pass the values in, or this is how addresses usually look. 0x is for hexadecimal, and this is the actual hexadecimal number itself. So if you say 0 hex, this number, that is what the address usually looks like. And you can pass addresses. So on this, I'm going to talk a little bit about C++, because this is what I learned in college. I learned about pointers and addresses in college, and I kind of want to share about that, so you kind of get to know and feel about it more than just what we learned in Java. I'll talk about Java's references later, but I'm going to go through each line of code here. So say here, we have a new integer. We have an integer A. We've constructed an integer A, and we've assigned it to a new integer. We've created a new slot in memory for the value 5. So I'm going to draw it over here. If we have a slot in memory, we have a 5 here. And we say A equals 5, right? So A equals 5. I'm going to also put the value down here, a equals 5. Now, B is a pointer, where we've created this little asterisk in the middle, right? There's a little star in the middle. And that indicates that, hey, this is an integer pointer. Similar to how we say this is an integer array, we've created a new data type of a pointer, where, hey, this is a pointer, it points to an integer. We could say, hey, pointer B equals also a new integer. So we've also created a new spot in memory, but instead of returning 5, it returns the address of where it puts 5. So we're going to make another 5 here. And instead of saying A equals 5, we're going to say B equals the pointer to that address. That make sense? And if I put this as address 0 and address 1, B should equal what? 1. Address 1. So I'm going to put 0 hex 1, just to say it's a hexadecimal location, some address. Not to confuse with integers. Does that make sense so far? B is a pointer that has the value of 1. Now if I say C is a pointer, C is an integer pointer, I can also assign that to B, where B is also an integer pointer. A pointer equals a pointer. That makes sense. They're both the same data type. So C will also equal B, where C equals the pointer to this function, this 5 here. So it references the same address location. So what would C actually be equal to here? Any ideas?
0x1.
0x1. Yep. 0x1. Because it's the same location. That make sense? We confused at all? We're good? Lively. Nice. Now, I can create another pointer, D, and I can say A. A is not a pointer. What is A? Just an integer. So we can use this ampersand to say, hey, go get the address of your data itself. So it gets the address of what A is. So D would say, hey, I'm also a pointer, but I'm pointing to where A is. What would be the value of B?
0x0.
0 hex 0. Exactly. Just like you said. Lastly, E. We've created an integer E, and it's not a pointer, but E equals this dereference operator, this star, saying, hey, go get me the value of what this location says. So it says, hey, go get me the value. It's a value storage. It dereferences the location, and it says, hey, E equals 5. E would also equal 5. Does this all make sense? So we can use the ampersand to get the address of the data. We can use the star or the asterisk to get the data from the address itself. So if I asked you to create, this is all majority pass by reference. If I said int f equals something, what would I say here to actually pass by a value? What can I say to pass by value? What's a value I can put there?
Repeat that again.
So what I would, if this is all pass by reference because we're using pointers,
Yeah.
in Java, what would I have to put here to make it pass by value?
Java.
Number.
C++ technically too. You're saying number? I'm gonna put A. Yeah, I heard you say A. Because now we would say f equals 5, which is a copy of what A is. Right? And that's passing the value of what it is. If we changed f, A won't change, even in C++ or Java. If we change f, if f is now 6, A won't be 6, because we're passing in a value, not a reference. Does that make sense? Peter, you okay there? Have any questions?
Well, if it was a pointer.
So if we pass in the pointer of A, so if we say this is asterisk and this is the ampersand. Yep. Oh, I did that wrong. Ampersand. Ampersand. If we pass that pointer in, then yes, this f would then be a pointer of this.
And then you can change that, right?
Then we can change it. So if we change f at that point, then A also changes. Make sense? We're good? Cool. So this is all how pointers would work and addresses work in Java, or C++. If I system that out that print B, what do I expect to see? Do you guys have any ideas? Yeah. I would see whatever the address location of that is. If system out that print B ampersand B or star B, what would print out? What do you think? Is that true? 5? And what if I did ampersand B?
0x.
No, it'd be an error. Because if I said the address of the address, impossible. So you can't do ampersand of a location or an address itself. Make sense though? Cool. I'm gonna erase this. So, moving on from that. Oh, there's one last thing I want to talk about. This is C++. We talked about Java. Third or second period made me talk about Python. And I had not known about Python. You were like, what? No. So when we briefly looked up, what do you guys think that Python is? Is Python a pass by reference, pass by value, or both?
Probably both.
You think it's both? Pass by reference? Any idea? Pass by reference? What do you guys think?
No idea.
No clue.
Actually, maybe reference. Pass by reference.
Peter, what do you think?
I think it's. Well, nobody's saying it's a pass by value.
Did you say pass by value? It is not pass by value. It's a similar to both. It does both pass by reference and pass by value, and more.
Uh-oh.
Whoa.
From what we briefly looked up, if you say A equals first and B equals first, in Java or C++, you would assume it looks like this, right? First and first. And A equals this, B equals this. You're going to assume it looks like that, right? In Python, it works like this.
Oh no.
Oh yeah.
Oh, it makes complete sense to you?
Yeah, it's
It doesn't make complete sense to me yet, but
I think it's because I recognize that.
it's like a dictionary.
Yeah, I kind of recognize like how you declare something.
So if we print the ID or the location of A and B, they'll be the exact same. And that they
That's
both
weird.
reference the same spot. But it's weird because we didn't do B equals A, which we would assume is the reference, right? We assume like it's a pointer to a pointer. What do you think?
If you change B, does it change A too, or does it?
My
like, create a new
assumption is that if we say B equals, someone said second last period,
Wow.
I think it would create a new one.
Yeah.
And say
Okay.
second
I
here,
agree.
Okay.
which is weird. It's weird. I don't know how it does it, but it interprets somehow on the back end to keep. It stores even less data because it stores two objects in the same place, even though they're not referencing each other. But I think it says it's a pass by object reference or assignment reference. I would look more into it if you were you. I don't know all about it, but that was one of the examples that I was like, whoa, that's weird. It doesn't make sense, but it does make sense. So that's Python. Python can do both. You can pass IDs or addresses they use them as, and you can do different things like that. So that's that. Now to look back at Java. Java does this. So we have string S1, similar to rectangle, where I would say this is potato. S1 equals this, right? But then I create S2. And S2 would not just be a pointer to this, it would be a reference to the copy of potato. So because Java is a pass by value language, we have to pass the value into this new piece of data. And we're copying it. Make sense? So we never see addresses. We can't see addresses in Java. We might be able to, but I can't figure out a way yet. Cool? Any questions? Cool. So given this, let's make a linked list. Are you guys ready? I know we've kind of sidetracked a little bit, but we're gonna learn how to make a linked list, and it'll make sense in a second. Because we need to know how addresses work. So I'm going to show you a picture of a linked list. This is a linked list. I'm going to show it to you for now, but the big things, I'll come back to this picture. The big things is that we have the value 15, we have the value 3, we have the value 17, we have the value 90. And it's similar to an array where we have all these values. In an array, what do we use to find these values? Indexes. We use indexes. We use an index to find 15. This is 0, 1, 2, 3. Different indexes. The difference here, we're using addresses. So we'll talk about that in a second. John Paul was like, what? What does that even mean? So the key elements to a linked list. One is linked lists are made up of nodes. So a node holds two values. It holds a data value and it holds a reference value or an address. I'm mostly going to be talking about addresses because it makes it a little easier to understand. You can implement these in Java with references as well. But it holds data and holds reference. And if this was an array, we hold data, we hold indexes. Same thing. Just a way to reference, way to get the data. In a linked list, we have a head, which references the first object, and we have a tail that references the last object. So the head, tail, we go through the entire list. That's that. We also have a couple key methods, as we talked about at the very beginning. We have an add method, and we have a remove method. And that the basic add method for a linked list creates a node at the end of the list. The basic remove method removes it from the start of the list. There are plenty more. There's insert, there's remove from a specific location, there's add to a specific location, there's add to the back. There's all these different things. Linked lists can manipulate their entire structure very easily. Now let's talk about it. So given all those things, we have one node here. We have another node, we have another node, we have another node. We have our head, and our head has an address in it. It's just a pointer. It has just a pointer, and it has an address in it, and it points to our first piece of data, our first node. Now our first node has a value, and it has the next node. Our next node has, this location has a value, and it has the next node, and the next node, and the next node until we get to null, where this will be the last part, or we have our tail pointing to this location as well. Do you see how we can only go, we have to start at the head and slowly go back our list? We can't go forward. That is one restriction of a linked list. But you can change that if you really wanted to. But also, what was I going to say? I just completely lost my train of thought. So you have these locations and you can kind of access these things. One question I have for you guys is, how would I insert a value here? What if I said I have a new node, and its location is the 4800, because we just created it. It's right after this guy. How would I insert this node right in between these two guys right here? You're thinking about it. What do you think? What was one thing I would change?
Like the method?
No. How do I insert one value in between here?
Changing the pointers?
Yes.
Where did you want?
Yes. John Paul, where would I change the first one?
You'd have to change the address of the 3600 one.
Okay, so we're changing this one. What do we change it to?
4800?
Sure. And what do I change next? You're about to say it. What's the last thing I have to change?
I forgot.
Anybody else have any comments of what's the other last thing that I have to change to insert this object?
Oh, you have to add 4,000.
Yes. If we put 4,000 here, now we've removed this arrow. We point to this guy and we point to this guy. Done. Fine. We've inserted an object into our list. It's super easy, right? Because we just changed, as you said, we just changed 2 pointers. Now, if you do this with an array, you're inserting an object, what do you have to do? You have to move everything back. You put an object in, you move everything down one. It's such a pain, exactly. But you see how quick it is to do this. It's similar in, are you okay?
I get it now.
You get it? It's, oh, that's what I was going to say. The big thing I was going to say is, this is a linked list.
Yeah, it's linked.
It's a linked list. It's linked by the addresses, right?
Yeah.
It makes sense when you understand it. And that they're all linked together, but we can manipulate these nodes and change how this list actually works. Right? Make sense? Cool. So yes, we can insert things. Array lists are similar in that we can insert things, but we still have to remove all of the addresses down, technically. Now my question is, how do I make a stack? And I'm gonna lay out a couple things for you. One, we have nodes, right? We have a bunch of nodes. So this is its own class. A node is a class, and it holds, what are the two things a node holds?
Content and address.
Data and address, or reference, whatever. Perfect, we've created nodes. Now two, we have a linked list. And linked lists have what?
Nodes.
They have nodes. I'm gonna skip nodes for now, but what else?
Head and a tail.
Fantastic. It has a head and it has a tail because it has to point somewhere, the front and the end. And the last thing I'm gonna add here is it has methods. In that it has an add and a remove method, right? Given all these, changing these, how do I make a stack? And let's think about what a stack is again. A stack is, what's the rule?
Last in, first.
Last in is the first out. Last in is the first out. And this is a stack of pancakes. The last one I made, I'm going to eat it first. It's lucky. So what can I change about this to make a stack? I'll be honest, we're not going to change the node. The node's just going to stay the exact same. So the first thing I would look at here is, where's my head?
In the front.
It's open.
What do you mean by front? What is front?
First.
First thing?
First note. Yeah.
Right here or here?
Bottom.
You're saying the bottom? Does anyone disagree with that? No one disagrees with that. Okay. Do we ever access this by itself?
No.
We never access this. Meaning that we never need a header or a tail there. So where's my head? It technically yes. We only need one, a head or a tail. I'm just gonna say we only need a head. And where's the head gonna be?
Top.
Very top.
How does that work?
So let's talk about it. If I have a stack of objects, one node pointing to the next node, and that these nodes always point to the next node, right? Points this guy, points this guy, points this guy doesn't have anything with it. Because we put it on first.
So shouldn't the bottom one be tail?
Well, we don't ever access the bottom one. There's no reason to access the bottom one. So when we have our head at the top, if we add object, bless you, if we add an object, that object becomes our new head and it points to the next one. We add an object, that one becomes the head, we make another one. Now if we pop an object, we remove it from the stack, it says go to this one, this is the next one. Point there, go to the next one. Point to the head. And we keep going down because we always have to do what? Push and pop off the top of the stack. And then we don't technically have a tail, but our head is at the top. Now what else do we have to change about these things to make it work? There's two last things we have to change. And there's only two last things on this list. Add and remove. So we have an add. Where does it add?
At the top.
Which is the head. We add to the head. Now where do we remove?
From the head.
The head. We have created a stack.
Yay.
Does that make sense? In that we add to the head, we also remove from the head. We have one head and we only have to point to the top object because that's the only one we can access. We can only look at that top object. We can peek at that top object too. Whatever it is, that's the data. But we're always accessing this one object. Does that make sense? So we've created a head. We just manipulated our nodes to access them in a different sense. Similar to linked lists, we go in one direction. Here, we change how it goes by saying we only have a head. We access it one way down or up. That's it. That make sense? We're good? Cool. Then my next question is, let's make a queue. Let's make a queue. Now, how would I now manipulate this to do a queue? So what is a queue?
First in, first out.
First in, first out is a line. Perfect. We have a bunch of little lines here. Now these are data, 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 data. You said first in, first out, right? Let's start. Where's our head? Any ideas? You think in the front? You're saying the front too? Anyone disagree? Say this guy's the head? Let's start with it. We'll start with it. We can come back and correct it later if we need to. Where's the tail?
the back.
We need to access the back, right? Do we need a tail?
No.
We don't need a tail?
Oh, we do.
What?
Do you think we need a tail?
Yeah.
Yeah.
So this is gonna be the tail, right? So now, where does our add go?
To the tail.
We add data at the back of the tail because we're adding to the back. And where do we remove from?
The front. The head.
First piece of data in is gonna be the first piece of data out. And we can keep hopping off the front, but we keep adding to the back. It's just like a line. People keep adding to the back of the line. People keep leaving because they finished the front one. So yes, now we've created a queue. We've done it. My question now to you is, what happens if our tail and our head are equal?
You don't have a line.
I don't have a line?
Yeah.
My size is either 0 or 1, right?
Oh yeah.
My size is either 0 or 1. If they're both null, my size is 0. Does that make sense? We've created a queue. We've created a stack. We've done it. So the last thing I want to talk about really quickly is that we've manipulated the linked lists. If we manipulate nodes, and that what if we have a node with data in 2 addresses? Now we can have a node with data, and it has 2 addresses to 2 children. Now it has 2 addresses to 2 children. 2 addresses to 2 children.
It's like a tree.
And now we're making binary trees, which will be next lecture.
Alright.
Crazy, spooky. I will not see you guys next week because there's a PSAT,
Oh yeah.
no.
but I'll see you guys the week after.
Oh yes.
So I hope you guys understand how we can manipulate nodes, and we can change these. These are a lot more free in comparison to arrays, right? A lot more free in that we can change nodes around, move nodes around. Cool.
Yes.
Thank you all. Have a wonderful day.